Project Hail Mary is likely my favorite movie of the year, and I truly appreciate how many people who aren't typically fans of science fiction have come to love the film. Like many stories in the sci-fi genre, the plot unfolds around a distant star located many light years away from Earth. However, unlike a vast number of science fiction universes, there is no such thing as a warp drive, hyperspace, or even those wormholes that were featured in Interstellar, which I have previously made a video about. No, the titular ship, the Hail Mary, must traverse the massive gulf between the stars at sublight speeds while experiencing the effects of relativistic time dilation. This is precisely why, when the protagonist sets his course back toward Earth, the computer informs him that the journey will take something like 3 to 4 years. Even though the physical distance is approximately 12 light years, he is undergoing time dilation, which slows down time for him and makes it appear as though the entire journey is happening much faster. The propulsion system for the spacecraft is fueled by a substance called astrophage, which is essentially a living organism that consumes the energy of stars, stores it up, and can basically hold more energy than anything else we can possibly imagine in the real world. It is extremely convenient if your goal is to fling a spacecraft between different stars at 99% of the speed of light. I have seen a great deal of discussion regarding all of this, the relativistic travel, the energy storage, and so on. However, I haven't seen anyone actually mention what the view would look like if you were really traveling at 99.5% of the speed of light. Now again, science fiction loves to depict things like stars turning into long streaks of light or hyperspace tunnels and all of that. But that is simply not the reality of what we are dealing with here. The stars are just too far apart from one another to ever become streaks. This is what it would look like if you were traveling toward the constellation of Orion at a speed of 1 light year per second. That is roughly 10 million times the speed that you would actually experience if you looked out the window of the Hail Mary at its halfway point. And this is the more realistic version of that view. Now, I know many of you watching are probably thinking, I think he just paused the video right there. And maybe you are right to think that. But at 60 frames per second, that means the very next frame of motion is expected to arrive in about 2 days' time. Stick around, I guess. But even with the total lack of motion in the stars surrounding you, there would still be some very obvious evidence that you were traveling close to the speed of light. I bet you are already thinking, oh yeah, the Doppler effect. We would see red shift and blue shift in the stars all around us. And this is just a simple visualization of that. It is not entirely accurate because at 99.5% of the speed of light, those objects in the red are being redshifted far beyond the infrared spectrum. And from the other side, these stars become incredibly bright. If you take an object like a star and you apply a red or blue shift to it, it is effectively the same as changing its temperature to the observer. At 99.5% of the speed of light, the objects directly in front of you have their effective temperature increased by a factor of 20, while those behind you are decreased by a factor of 20. So the sun would be about 290 Kelvin, which basically would be the same temperature as the Earth. That looks fine in infrared, but it is basically not emitting any visible light on its own. And so, it was at this specific point in the story where I thought, oh, I'll mention that in Star Trek. During their warp drive scenes, they used to stretch out their stars into different colors. This was supposed to be a reference to the Doppler shift. But then I looked for some actual images on the internet and realized that no, they weren't actually doing that at all. They were just doing whatever the VFX artists thought looked cool at the time. So, yeah, I guess I just remembered it that way because I was a physics nerd rather than actually paying attention to the screen. Now, far fewer of you are likely familiar with the effects of aberration. This is where, as you accelerate faster and faster, the world kind of distorts all around you. If you look behind you, the world seems to start getting magnified. And if you look ahead of you, the world actually seems to be shrinking. So naively, it looks like while you are accelerating toward your target, it appears to be getting smaller and further away. This is a direct consequence of the fact that light moves at a finite speed. As you are moving through these photons, you are encountering them at an angle which depends upon your velocity relative to them, right? It is a vector problem, right? It is just like you are flying through space and you suddenly hit this photon which is coming from the side, But because you are going forward so fast, it seems to come from ahead of you. It is the same as driving a car through a rainstorm. You see more rain hitting the front of the car than hitting the sides or the rear of the vehicle. The difference being that the car typically is going faster than the rain, whereas with the speed of light, you can't actually go faster than it. While I am talking about this, in this sci-fi world of interstellar travel, regular astronomers have to deal with this every day, or at least every night, because, they do things at night. But yeah, the velocity of the Earth around the sun is 30 kilometers per second. And that means there is a 60 kilometer per second difference between the 6 months separating the orbit. That means that light from distant stars finds itself bent subtly by this velocity of the Earth around the sun, and so you have to subtract that out if you are doing high-precision astrometry. Anyway, this simple diagram shows how light rays coming from different angles have their apparent position adjusted based upon the velocity. And as you go faster and faster, more and more of the objects appear to be coming from in front of you as you get up to really, really high velocities. It appears that the entire universe gets sucked into a circle just in front of your spacecraft. But there is another part to this because as these light rays are getting closer and closer together, that is kind of like magnifying them. If a patch of the sky that is, say, 10 degrees by 10 degrees gets squished down to, say, 1 degree by 1 degree, that means you have got the same amount of light coming from 1/100th of the area. Therefore, it has to be 100 times as bright. So you get what is called the searchlight effect, right? A beaming effect. And not only is the light getting brighter because of this, it is also getting blue shifted and therefore much, much brighter still. And to help visualize this even better, there is this project on GitHub by Dmitry Levo which demonstrates this. On the left side, you set your acceleration and it will simulate, 1 year per second of time lapse. Now we are passing 60% of the speed of light, and the stars ahead of us are definitely starting to get brighter. And in the bottom right, you can start to see that there is some time dilation effect. Our ship time is getting behind the world time, which means we are aging more slowly. As we are getting up to 95% of the speed of light, the stars ahead are all looking super, super blue. Our time dilation is getting stronger and stronger. And again, the world is condensing into this small area in front of us. Everything that disappears from that is getting redshifted beyond what we can see. And of course, the visible light that we see, while it is getting blue shifted up into the ultraviolet, we can't see the infrared that is also getting shifted up into the visible. So we never run out of stars. The stars never disappear on the blue side. It is only on the rear side where they are getting redshifted to below zero. Now, as we start going faster and faster, we will start to see things that would just be too faint or too red for humans to see normally. Things like nebulae that may be glowing in the infrared. And yeah, even although you are setting constant acceleration, we can never actually reach the speed of light. The mass of the spacecraft increases due to relativity, so the amount of acceleration gets smaller and smaller as we get closer and closer to the speed of light. But yeah, as I said, some of those faint things like nebulae and stuff are now getting bright enough that we can see them. And eventually the cosmic microwave background radiation, which is normally at 2.7 Kelvin, is now getting raised to a temperature where it glows red. And as we go faster and faster, it too starts to get blue shifted way up until it is a shining light. We are staring into the remnants of the Big Bang itself. I hope you brought your sunglasses. But coming back to the Hail Mary, it isn't nearly so fast. It is only going 99.5% of the speed of light at the halfway point. But I did want to give an idea of what you might see if you poked your head out when it was traveling that fast. And this is a basic render in Blender, like so. The model comes from a model website. I think it is originally based on a Juno New Origins build, but the skybox, it comes from Space Engine. It has been processed with my code that generates the aberration and the blue shifting. I had to actually dial down the beaming somewhat. Also, the route between Sol and Tau Ceti pretty much is perpendicular to the disk of the galaxy. So you end up seeing the entire disk of the galaxy as a ring in the sky in front of you. The redshift angle also kind of dialed down a bit so that you could actually see that there was some texture behind the spacecraft. And so while I used a single still image for that skybox, I did actually create a visualization of what it would look like as you were traversing the distance between Sol and Tau Ceti. So yeah, it is actually a 360 render, But those 360 videos never seem to get as much interest as I would like. So I will share those in links so that you can actually stick on your VR headset and point your head wherever you like. But for now, again, you can see how the galaxy, which was out my side windows at the start, is now collecting in front of me and getting very, very blue. And again, I have scaled down the beaming here because I don't have enough HDR capability inside the video player inside YouTube. Understand that this would be hundreds of times brighter than the image behind you. By the time you reach 95% of the speed of light, the light from all the stars in front of you is about as bright as a full moon. Once you are at 99.5% of the speed of light, the light is something like 100 times the brightness of a full moon, so it is equivalent to a well-lit room. But the average temperature of that light is so high that it is beaming lots of ultraviolet at you. So you would get a sunburn really quickly. And now we are about the halfway point. We are about to hit top speed. And as soon as we get there, we flip over and we start decelerating. And now the decrease in the aberration means that it looks like we are getting closer to our target. So all this is to say that while Project Hail Mary didn't need any sci-fi warp drives to travel between the stars, space is still going to look pretty warped to an observer traveling at 99% of the speed of light. If this exploration of the physics behind the journey has changed the way you look at the stars in the night sky, please subscribe and like the video. We are constantly working to uncover the scientific history and reality that often remains hidden behind the curtain of fiction. Help us plant the seeds for a more informed future. Our next deep dive into the treasures of the cosmos will be opening very soon.